Good afternoon. All right. If I could have your undivided attention, and we're going to jump right into molecular orbital theory. And we want to have a soft landing, not a hard landing with this. So the last time you heard that there are bonding and anti-bonding molecular orbitals, and that there are two kinds of bonds so far that can be formed: sigma bonds and pi bonds. And the sigma bonds can be formed with s orbital overlap, and also if a certain p orbital overlaps, then you can have a sigma bond. And pi bonds you only can have from two configurations of the p orbital. Let's go a little bit more into detail of that. So we had the two s orbitals overlapping, and we started with hydrogen. There's a one electron in each of the 1s orbital. And so you form a bonding molecular orbital. You see they're in phase here. Then you have constructive interference. With this you have bonding, and this is how that bonding sigma molecular orbital looks like. And you also can form, and you have to form, anti-bonding molecular orbitals, because you have one s here and another s here, and you form one bonding molecular sigma orbital, which has a sigma bond here. So you cannot lose orbitals. You started out with two, and so far you only made one. That's the bonding one. So the other one will be the out-of-phase interference, the destructive interference, and there you have anti-bonding, an anti-bonding molecular orbital. Anti-bonding says that there can be electrons in there, but it's not bonding, all right? So, and you know now, if you have nodes or nodal planes, that you are higher in energy compared to a structure that has no nodal planes, to an orbital depiction, okay? So with this, the sigma bonding would be lower in energy than the initial 1s electron, all right? And the sigma star antibonding is higher than the initial 1s electron in energy. This is our energy scale here. You always have to assume this is the energy scale. So if we fill this with, for example, with helium, helium is 1s2 configuration, each helium. So we need two helium atoms we need to bind together, okay? And so you have to have a bonding molecular orbital and an anti-bonding. And since we only have s atomic orbitals, so we can only have sigma bonding. So you follow now the Pauli principle and Hund's rule. So you put two in here, one here and one here, anti-spin. And then we have two more left. You put them in the anti-bonding molecular orbital. Then we talked about a bond order. The bond order gives you the strength of the bond. Or if the bond order is 0, if this bond is at all happening. So you have the bond order is the number of bonding electrons, which is 2, minus the number of anti-bonding electrons is also 2. 2 minus 2 is 0, and we divide this by 2, so 0 divided by 2 is still 0. What's the bond order? 0. What does this tell you? It tells you it doesn't bind. Helium doesn't form diatomic molecules. It's just helium by itself, okay? Now, lithium, we go to the next period. So we have that helium is full here. There's no bonding. And then we go to the next period, and there we have lithium has one s2 electron, or 2s electron. 1, 2s1 is the configuration. And we take two of those, and we have to put them in the bonding sigma molecular orbital before we can fill it in the antibonding. Since we have only two, that means the bond order would be 2 minus 0 divided by 2 is 1. So this is possible. Lithium can bond to each other in dimolecular atoms of the same type, or lithium to lithium. Now beryllium is 1 over, is a 2s2 each beryllium, and we have now 4 electrons. 2 go in the bonding sigma, and 2 go in the anti-bonding sigma. And with this, we have a bond order of 0. Doesn't exist. Excellent, you got it. So I wrote you down the bond order one more time. And now we come to that special case. And this was a little confusing for some of you. The special case is that you have sigma and pi bonding. You only can have this with p orbitals. Okay? If you have p orbitals, they can overlap in 2 different ways. And the way they overlap will determine for you what kind of bonding it is. Is it sigma or is it pi? So we have this orbital here. I'm now p. This is the p orbital here, okay? This goes in this direction. What we call that? That's the x. Isn't that right? Yeah? And then we have this goes in that direction. That's the y. And then we have this in this direction. That's the c. All right? So now I have 2 of them. If I have one like this and another one like this, so if I stand over there, then that would be the other one. Okay. So I'm playing 2 things at the same time. So they would overlap here, and they could form a sigma bonding and a sigma anti-bonding bond. So these are the ones, when they are in phase, I call it head-to-head, like you would lay here, one head here, one head here, one toe here. There's one p orbital head-to-head or toe-to-toe. That would be constructive interference, would be bonding. And if you have head-to-toe or toe-to-head, then you would have anti-bonding, okay? So this is the only configuration where you can get sigma bonding with p orbitals. This is the p, what is it? The p y orbital in our dimension, yeah? So now you have 2 p orbitals left. One goes this direction and the other this direction, okay? So let's see, this is the other binding partner. Here's one binding partner, has 1 p orbital, the other is here. So they can overlap here and they can overlap here. So if I'm the whole p orbital, I'm now 2 p orbitals, okay? They can overlap head-to-head, toe-to-toe, constructive or vice versa, destructive. Now with this, you have now a pi binding, pi bond. That's the pi bond, which goes side by side. So there's one more, which goes out of the plane in the x-axis. This can overlap here, and this can overlap. So this is 2 of them, of course, have to overlap. One comes from one atom, and the other from the other atom. So now we have a pi, that would be a pi x, and this would be a pi z. Okay? How many electrons can you have in a pi z? 2, of course. And then the pi x, 2 also. 2 bonding each and 2 anti-bonding each. All right? So this is, I showed you here the configuration. That's the pi y. What kind of bond is that here? Sigma. And this here? And this here? Okay, you got it. So this would be, and here I show you just the 2, the sigma and the pi. I'm omitting one of the other pi's. So the pi y, that's the one head-to-head, toe-to-toe, okay? Here, this would be the bonding, that's constructive interference, would be bonding, and this is the bonding molecular sigma orbital, okay, of the py, py. And it has 1, 2 nodes. And we know also, since we have 2 orbitals, we need to make also an anti-bonding one. This would be head to toe, okay, or toe to head. And this would be an anti-bonding one. It has 1 node here, and it has a nodal plane even here. You see that? So which one is higher in energy compared this one or that one? Is this one higher in energy? Okay, why? Has more nodes. Very good, okay? So now we have discussed how we get the sigmas and the pi's from p orbital overlapping. But remember, we only have 2 of the same atoms overlapping, all right? Atoms binding to each other. For example, nitrogen or carbon to carbon or oxygen to oxygen. And this is, again, the depiction of this here. This is the sigma bond, and this is the out of phase now. This is the destructive interference, that is sigma star. And then here you get the px and the px here. So this gives a pi x bonding and a pi x antibonding, and the set gives And Z gives the pi C bonding and the pi C antibonding. So you have 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here. They're anti-spin in there, all right? So you don't necessarily have 2 electrons in the antibonding, not even in the bonding necessarily, because you might not have enough electrons, right, from the molecule or the atom you're looking at. So I have talked about this the last time here, and if I could have this on the screen up there, please, if you could get the left side up here, if that would be possible. So and then I'm now asking you the question. We have the ionization and the electron capture. So this would be an ionization. This would be N2 plus, and this would be an electron capture, that would be N2 minus. So I'm asking you now, which is true of the bond strength of the product? So bond strength is bond order. And I also tell you, and I have told you before, that there are fractional bond orders. Okay? Don't get confused. Fractional bond orders are fine. So now I have given you here actually nitrogen already, all right? So you have to take an electron away or put an electron in it, then determine your bond order, and then compare them with each other. Right? Let's see if you can do that. Can you read in the back the question down here? You're going to be okay? Can you hear me okay? Good. And you can see the nitrogen up there, yeah? So the answer is right up there. If we could get now the question back up there, please. Thank you. So you see, now you have it here. Can you read it from the back there? Okay, good. There's the nitrogen. $246 people here. Wow, must be coming close to midterm. But that's not so close to midterm. All right. You know what bond order is, don't you? Okay. Number of bonding electrons minus the number of antibonding electrons divided by 2. All right, now let's go and have a look at this again here. Please follow me here. So this is nitrogen. If you take one away, you have ionization. Then you count the number of bonding electrons and subtract the number of antibonding electrons and determine the bond order, all right? Or you have N2 minus, so you put an extra one in there. Count the number of bonding minus the number of antibonding and divide by 2, and then compares to the number that you got before when you had the N2 plus. All right? Why not discuss it with each other? You really need to know that. At least Monday in a week. The bond order of this is 3, isn't it? Now you take one away. What's the bond order? 2, 4, 5. Huh? 5 minus divided by 2. And you add 1 here. So you have 5 minus 1 No, 6 minus 1 divided by 2. What is it? Yes. Yes, we're getting better. But only slightly, though. So let's say that B is right, okay? Now, the bond order of nitrogen is number of bonding electrons, 1, 2, 3, 4, 5, 6, minus the number of antibonding, 0, divided by 2 is 3. It's right there. Order is 3, okay? Now, let's add an electron. So we have decided what the bond order, that's the bonding ones, and these are the antibonding. They are empty, the antibonding. So the bond order we decided is 3. So now let's add an extra electron. So that goes here, all right? So this is bonding, 1, 2, 3, 4, 5, 6. Minus 1 is 5. Divided by 2 is what? 2.5, okay? Is 2.5. So now we want to have the N2 plus, we take this one away. Okay, so we have that here then. See that? In the bonding, there seems to be some dashes missing, but that's okay. So you have one, the virtues of Microsoft. So you have 1, 2, 3, 4, 5 bonding minus how many antibonding? 0 divided by 2. What's the number? 2.5. And so the question was, what was the question? What was the bond order or the bond strength of this or that? Is it this one larger than this one? Is it about the same? Or is this one smaller than that one? You know what this sign means? Approximately, about, okay? Maybe that was the problem. So with this was the answer, okay? So today we're going to talk about further molecular orbitals, and we need to accommodate other geometric structures. What do I mean by that? I mean, so far, we only have looked at homonuclear atoms, okay? They have 2 of the same kind, they bind to each other. And the only angle that we could accommodate was 90 degrees, because they were either parallel to each other or 90-degree angles, all right? That was all the bonding we could do. But this doesn't help us a whole lot. For example, we look at carbon here. We have the carbon, we want to bind something here, and we want to bind something here. And we know there is a triple bond here. What would be the steric number on that carbon? 2. What's the bond angle? 180 degrees. Example, acetylene. Okay, now we have a carbon that has 1, 2, 3 things attached to it because there's a double bond here. What's the steric number? 3. What's the bond angle? 120. An example, for example, what would that be? That's graphite. Graphite comes in layers. So it's layers. So you put graphite on your pencil, you put a couple of layers on your paper. That's how it works. It sheds off some layers. That's how you write. So there is no, but the layers are not connected to each other. If they are connected to each other, then we have diamond. Okay, we have the diamond structure. And so that would be, you have 1, 2, 3, 4 bond partners, 4 things. What's the steric number? 4. And what's the angle? 109 degrees. And this would be polyethylene. You see, you have that linear structure here, that in one plane, and it's connected to this here. So wouldn't it be great if graphite would be as valuable as diamond? So we all the the pencils that you have, they would be fantastic, and you would wearing pencils in your earrings and stuff, or you wear this graphite pencil ring, and then you poke yourself accidentally in the eye, and that would be not so great, okay? You know now the difference between graphite and diamond, and so there's definitely the bond angle is the difference, and that extra very strong bond between the layers. That makes the difference, okay? And no pencil earrings. Nevertheless, there are people probably who wear pencil earrings. So probably next time I see somebody with pencil earrings. So the point that I'm trying to make here is not about graphite and diamond. The point that I'm trying to make there is no way that we can accommodate something like this or like this. This maybe we can accommodate with S and P coordination. But we can't accommodate this with the molecular orbitals that I've shown you so far, because they have only 90 degrees. They are S and P. So how do I get an angle like this here? So what I do, I use a linear combination of these orbitals at the atom. No binding. We just combine the orbitals at the atom so that we can accommodate the steric request, the steric requirement. And how we do this, we make hybrid orbitals, and this is mathematically possible. Quantum mechanically, it's possible. And with this, for example, we make an sp hybrid orbital. That S shows you there's one s orbital and there's one p orbital. And so we don't do any bonding. We just look at that atom and get the orbitals ready for binding by doing an sp hybridization. So we have one s orbital and one p orbital, and now we make an sp orbital. Of course, we have two orbitals. We need to come up with two sp orbitals. Okay? And these are the phases here. This is your central atom. There are one points in this direction and one points in that direction. With this, now you could accommodate steric number 2 easily. So you have two sp orbitals, and this is how they really look. Okay? And so you could, this is your atom. In this case, it was our carbon here. It could have a triple bond, for example. Or you can have here some bonding and here some bonding. So you can accommodate a bond angle of 180 degrees, but you can bind to two different partners here. And a steric number of 2. So that's the sp hybrid orbital. One s and one p gives you two sp hybrid orbitals. One points in this direction, the other in the other direction. Okay, 180 degrees. So now you probably can imagine how we're going to get the next one. The next one would be steric number 3, so we want something flat and with a 120-degree angle in between. So obviously we need 3 orbitals. So we take one s and take 2 p's. One s and 2 p's. So what we make an sp2. That shows us how many p orbitals we have used. So we have 2 to make that new hybrid orbital. We have no bonding yet. We're just getting it ready for bonding. So there's this hybridization of the atomic orbitals. So this would be 1s and 2p, so this sp2 hybridization. How many sp2 orbitals would we expect to get? 1, 2, 3. We got to get 3 sp2 orbitals out of this, and this is how they look. Okay, each individually. And if we have 3 sp2 orbitals, and if we put them together, there's your central atom. So one points in this direction, one point in that direction, one points in this direction. So the bonding can happen with this, and with this. And with this, what steric number do we have? 3, and the bond angle of 120 degrees. Okay? So that's the sp2. Now you can imagine how we probably getting to sp3 hybridization, and it shows you right here. So you use another p orbital, 1s and 3 p orbitals. There they are. You get how many sp3 orbitals? 4, okay. You have 4 sp3 orbitals. How would they be oriented in space? Tetrahedral. This points towards the corners of a tetrahedron. And there at the corners, the binding happens then. So with this, you have a steric number of 4 and a bond angle of 109 degrees. Now let's assume that you have 2 free electron pairs here. What would be the bond angle? No, 104.5. What is if you have one free electron pair here only? 107. And so if you have no free electron pairs, it's 109 degrees. Good. So we have solved that now, and we can all go home. No, we need to do the binding now, all right? So this is what I just told you. The hybridization for this would be sp. For this would be sp2. That would be planar, trigonal planar. And for this would be sp3. So that what you can do with s and p orbitals. So this would be the tetrahedral orientation or coordination or hybridization. So you all have heard of benzene. This is C6H6. And the carbons are bound to each other. You see that? The carbons are bound to each other. There's 1, 2, 3 partners, 3 bonds here. And this forms a hexagon, all right? So I want to know what is the hybridization of that C orbital, this carbon here in C6H6. Is it sp, sp2, or sp3? So this one I want to know. You can also use that one, or that one, or that one, or that one, or that one. I want to know what is the hybridization of these carbons in benzene. Why don't you think about it and give me your answer? The first thing is you need to think, what's the bond angle here? Okay? Think of the bond angle. Maybe that would help. In order to put a hexagon together, what would be the angle of each of them be? Okay? They all have all the same angle. Yes! Excellent! Excellent! Very good. Very good. Perfect. So of course you know this has to be 120 degrees. It's flat. It's planar, trigonal. So what's the number? What is it called? The steric number is what? 3. Okay, it's right here. So that is 1 s and 2 p's. Give sp2. 3 sp2s. Remember, there's 1 p left because you have 3 p's. There's 1 non-hybridized. We're going to talk about this in a little while. Okay? Now you have that bonding in that plane done, but this is not the whole benzene story. And we're going to talk about this in a second here. So the steric number was 3, and the bond angle is 120 degrees. And with you have the sp2 coordination flat. So there would be here, there would be the next one. The next carbon would be here. It would be the hybridized here and hybridized here. That would point towards this. So that would be the bond here. What would that be to the next one? How would you call this? An sp2, sp2. And here would be the hydrogen. The hydrogen has what kind of orbital does it have? S. So that would be an s, sp2 bonding. Let's see, there's the hydrogen, there are the carbons. Of course, the carbon needs to be sit here and has to have these lobes here from that overlap here. That's not very well drawn. But so you have an sp2, sp2 hybridization between the 2 carbons here, bonding essentially. This S from this is an sp2 lobe, and from this is an sp2 lobe. They overlap, share the electrons, and with this you have sp2, sp2. Now this one we decided, this is an sp2s, okay? The hydrogen is not hybridized. It doesn't have to hybridize. Overlaps very nicely. And with this, the answer was B. So now we come to multiple bonding. Ethylene. Ethylene. What is ethylene? What's the formula for ethylene? So I take offers here. What's the formula for ethylene? C2H4? Okay. I agree with you. Okay, C2H4. All right. So we have one carbon, and one carbon needs to bond to each other. Okay? And it needs to overlap. All right? So, and then we have how many hydrogens? 2 more hydrogens we have. Yeah? On each carbon. So that means what's the steric number on that? 3. So you would have a hybridization of sp2. Okay? So you have sp2 here. This is 1, 2, 3 lobes of the sp2. And you have here on this carbon here also sp2. 1, 2, 3. And they overlap here to form what kind of bond? Sigma bond. Exactly. But now you see that red and green here, there's an extra p orbital, which we haven't used in the hybridization. There are 3 p orbitals, obviously. So now the electrons say, oh, we want to use that p orbital also. We not only have sp2 hybridization, but we also use that p orbital for binding. And with this now, you have this overlapping here, and you have this overlapping. What would you get? You get a bond. And what's that? Is that a sigma or a pi bond? That's a pi bond. Okay. So with this one, we form the sigma, the sp2, and this forms the pi, because it's the p orbitals overlapping. All right? And so we only have one each left. And with this 2p z orbitals, that was the z, that's the direction, form a sigma bonding and a pi bonding and a pi anti-bonding. Let's forget about these anti-bonding. Of course, if you have bonding, you also have to have anti-bonding, but it becomes too complex for you, okay? So just that you are aware of this. We just talk about the bonding at this point. So this was this here. That's the sigma bond. And now that's the sp2. sp2 plus minus, of course, constructive and destructive, but we just doing the sp2 plus sp2, that's constructive overlapping and interference. And then you have the sp2s, that's sp2 here, and the s has from the hydrogen. sp2 is this here, and the s from the hydrogen, sp2s bonding. Okay, so we have 1 sigma bond, 2 sigma bonds, 3 sigma bonds, 4 sigma bonds, 5 sigma bonds, isn't that right? Okay, and then we have this here, and what is that? That's our pi bond, and that comes from the PC. So how many bonds do we have? How many sigma bonds? 1, 2, 3, 4, 5. 5 sigma bonds, and how many pi bonds? 1. 1 pi bond, all right? So this is how we can do the multiple bonding, and we have a double bond in this case, and they are not equal. There is the sigma and the pi is stronger than the sigma. Not double as strong as the sigma, but it is stronger. So now you need to show me everything you got, all right? So we have this molecule, it's lactic acid. It was believed to be making this muscle pain after extraneous exercise. Actually, it's not, but it's a totally other story. It's not lactic acid what causes this. Anyhow, so I want to draw your attention to this bond here. You have here carbon, and a double bond to oxygen. There's 2 free electrons, okay? And here you have an oxygen. There's 2 free electrons here, 1 bond here and 1 bond here. I want to know what makes the bond here. What kind of a bond is this here? Okay, so you need to find the steric number of this one, find the steric number of that one, find the hybridization, and then overlap it and tell me if this is an sp on the carbon and an sp on the oxygen that overlap, or is it a pc on the carbon and a pc on the oxygen that's overlap, or is it an sp2 on the carbon and an sp3 on the oxygen that overlap. So now you have to show everything you got. All right, let's start with this. So first you determine the steric number, then the hybridization, steric number hybridization, and then you can answer this here. Got it? Okay. You look unhappy, so I think maybe I don't get it. Is your clicker working again? You forgot your clicker. Wow. Consider yourself that I have not asked that question. All right. Yes! Excellent! Excellent! Wow! There we go. See, you're getting the hang of it. That's wonderful. Of course, this is the steric number 4. You have 2 free electron pairs, 1, 2, 3, 4. So you need to have a tetrahedral orientation. Okay, and tetrahedral you get with sp, what is it? sp3. 3 p's. Is that tetrahedral? Do we need yeah, sp3, okay. On the oxygen. With this, actually, we have the answer already. We don't have to continue anymore if you have this here. But let's look at this here. What's the 1, 2, 3 is the steric number, isn't that right? So what would the hybridization be there? sp2, so that would be sp2 on the carbon, sp3 on the oxygen, so that would be not such a linear thing necessarily, because this one is not linear. And so you have an sp2 on the carbon, sp3 on the oxygen, and this was the right answer. Excellent, excellent. So let's look again at nitrogen. We know nitrogen has a triple bond, but nitrogen itself has a free electron pair, isn't that right? Okay. So how would we do that? We need to bind the nitrogen here together, okay? So we do an sp hybridization, 1s from this here, okay? From the 2s here. And we hybridize this with 1p, all right? So make an sp2, so now it's 180 degrees angle. We can bind here and we can bind here. So we put the free electron pair here in here, and we overlap here with those guys, with the other one, to have an sp sigma bond, and this would be the first bond. Okay, so we have 1 sigma. Now we need to talk about these other p's that are not hybridized. Okay, so this is the py, and this is the p. That's the px, exactly. It comes out of py and px. Okay, so they overlap. Each of them overlapping with the appropriate other one. How many pi bonds do you get? Bonding pi bonds. 2. So you have 1 sigma and 2 pi bonds. With this you have a triple bond. Okay? 1 sigma and 2 pi bonds. Triple bond. Now let's look at the sigma bonding again in benzene. You see this now. You have already solved this. This is an sp2, sp2 overlapping here, sp2 overlapping. This is 120 degrees. We know this is child's play now. Okay, and this is sp2s coordination or bonding. So now we come to finalize the bonding on the benzene. We have so far we have made that ring with the sp2, that hexagon. But we had sp2 that means there's one p orbital still left. That is the kicker, that p orbital. And the electrons want to use that p orbital also. And so with this would be the py orbital. They're standing around here, the py orbitals. And so now they overlap constructively. And they form a pi bond. You remember the sp2, you had the p bond here, the sigma bond. And then you have a pi bond on top. And this bond is delocalized. It's smeared all over the molecule. We call this delocalized electrons. So there's like a halo of electrons around. There would be a religious thing, for example, what could use. I'm not allowed to do that. But halo would be the right thing. Yeah. So there would be all over the electron density, all over the molecule. And so now you have sigma and pi bonding, and this completes the bonding in benzene because you have this double bond, and this is written that every other bond is there only, okay? So you have every other bond is a double bond, and so actually it's a delocalized mesomeric structure, all right? So let's continue with benzene, and we look at the delocalization of electrons, or the resonance, and so this would be one possibility, that they are all constructively interfering with each other, and they would form here one possible energetic constellation. So this is how this looks like. There's, of course, the other possibility that half of them are in phase and the other half are out of phase. So then you would have here, what would you have here? You would have a nodal plane. So that would be an energetic situation different from this what I have shown you before. So let me ask you the question now. There's the nodal plane, and it's also one delocalized, one in the constructive, one destructive, actually both constructive. So I'm asking you now, which molecular orbital in benzene formed from the atomic orbitals, okay, has the highest energy? Which molecular orbital in benzene formed from the atomic orbitals has the highest energy? Would it be this one, or this one? Why don't you think about it and give me your answer? Yes? Why are pi bonds higher in energy than sigma bonds? They bind stronger. I didn't say that they are higher in energy, bind stronger, okay? If they're stronger, bind stronger, they would be actually lower in energy, okay? But that's not the question here, okay? You sure that B is right? Yes, you're sure? Okay, too bad. Let's do it anyhow. Let's make a demonstration here. I need 2, 4, 5, 6 carbon atoms, please. Come on up and form benzene here. Let's form benzene. So it's a hexagon. Come on up here. One stands here. You're going to be here. You're going to be here. You're going to be here, please. So then we have 2 here. 2 here and 1 here. Not so close. Okay. So why don't you turn around and greet your fellow students here? So this is our hexagon, yeah? This is benzene. There's 1, 2, 3, 4, 5, 6 carbons there. If you raise your right hand, okay, all of you. So now they are in sync. They are constructively interfering with each other. You see any node here? No, there's no node, okay? Now if you raise your left hand and put the right hand down, and you also. You see any node here now? Obviously they are out of phase, okay? And these guys are out of phase. You see that here? So the node is where? Right here. It's the nodal plane, okay? You agree with me? How about you? Raise your right hand now, the left hand. And you also raise your left hand, okay? So how many nodal planes do we have now? We had this one was established already, okay? Now, do we have another one here? There's another one here, okay? All right. Is that correct? Do we have a third one maybe? No. Let's make a third one. So up, down, up. So this got to go this one here, okay. This one is fine. This one and this one needs to change. I need to have this one here. Is that right? Okay, up, down, up, down, up, down. Okay, so how many planes do we have now here? 3. One here, one here, and the third one is here, isn't it right? Okay, now answer the question again. Give your colleagues a hand, thank you. And answer the question again. Which one has the highest energy? So everybody gets it now. Which one was the last configuration? Left, right, left, right, left. Okay? Sounds like square dance. You probably don't even know what that is. Huh? Left, right, left, right. Do, si, do. Swing your partner. Actually, when I was 20 or something in Germany, I took square dance lessons. That's kind of the picture I had from America at the time. It was a very different picture when I came here. Not from America, the picture of America. Okay, don't forget to click in. Alrighty, let's display it. If it lets me display it. I think this is spite. Isn't it? Okay, of course the one with the largest number of nodes. And this would be, the more nodes, the higher the energy, the less bonding character, all right? So this would be, this is 2 here, and this is 3, as I've demonstrated to you. Wait, something important. So far we have come to steric number 4, but we couldn't do steric number 5 and 6 yet. So now you need to use the d orbitals. How many d orbitals do you have? 5. So if you want to have a steric number of 5, what would that be? Trigonal bipyramidal. So you need an sp3d. Okay? Or a dsp3. You can do that also. How many d's you have left that are not hybridized? 4. And now we come to number 6. That would be the iodine trifluoride, for example. Number 6 is octahedral, what do you have? D2sp3. D2sp3. How many unhybridized d orbitals you have left? 3, okay? And this would be, for example, sulfur hexafluoride. And with this, or xenon tetrafluoride. And with this, I see you on Wednesday.